Well, first of all, it's a pleasure to be here in person for our summit and see our colleagues and friends from universities and energy simulation. So it's really a great day for us. And today my talk is about modeling and simulation of deformation bands and natural fracture network effects on fluid flow. So I'm going to show you a few numerical simulations. And some of them is coupled geomechanics, coupling the geomechanics, and in two based on outcrop data, two different outcrops. One referred to a sandstones crossed by faults, so that is where we found the deformation bands, and the other one is a fractured carbonate outcrop that we both are analogous to the Brazilian reservoirs, and they are about 800 kilometers from my city, Recife, where is our main campus at UFPE. About the chair, the title of the chair is Reservoir Modeling and Robust Optimization. The main areas are geological modeling and reservoir simulation. We understand as reservoir modeling the outcrop characterization, upscaling, geomechanics, carbonate and CO2 geochemistry, laboratory testing and constitutive modeling. And we apply robust optimization to WAG optimization, uncertainty modeling, and optimization with geomechanics constraints. Of course, the proposed research can be applied to both IOR and CO2 injection storage for CCS projects. And we are especially interested in what happens when CO2 is injected in a formation, and a carbonate formation that that will be followed by water acidification, mineral dissolution, and change of porous permeability, and also change of the geomechanical properties of the material, stiffness and strength. So we will have two posters here in the poster sections presented by Jimena and Katia. Katia will present the results of injection of CO2 in synthetic carbonate rocks and the change of properties, including geomechanics. And Jimena is presenting a very interesting shear test where acid injection is promoted inside the fracture. This was developed at KAUST, and where she did part of her PhD. So in the presentation, the topics that I will talk about in our chair is outcrop characterization, the components of the chairs, the outcrop characterization, upscaling, geomechanics. So we think that models that predict permeability by considering analogs were used to enhance the understanding of the relative contribution of deformation bands and fracture networks. So, to the reservoir quality. So, as I mentioned, we have the Brazilian post-salt that are faulted reservoirs made by sandstone. So we have in this type of reservoirs, the deformation bands that are subseismic brittle structures associated with the process of faulting and formed by grain rearrangement and strain softening. They are located in the core zones of a geological fault. In our conceptual model of geological fault, we have a core zone surrounded by damaged zones for fractured rocks. And the question that we would like to answer is, do they really act as partial flow barriers? So to answer this question, we are going to perform flow-based upscaling of a very high fidelity model of the deformation bands based on the analogs. And the other topic of my talk is the analysis with discrete fracture network related to the Brazilian pre-salt carbonate reservoirs. The idea is to capture the relationship of the fractures in the fractal system. We are, in this case, especially interested in topological aspects of the fractal network. So the topology to represent connectivity aspect of the fractal planes. We have 3 PhD students working this area, and it is the question is the influence of fractures in interconnection degree or the topological patterns important to equivalent permeability of the fractal medium. So we are going again numerical upscaling, flow-based upscaling based on outcrop data to try to answer or to put some information in this on this topic. Another important component of the chair is that is in the methodology that I'm going to use is the numerical modeling. By the way, we have another 2 posters. One poster will be presented by Tulio, that he is working in a similar model that I'm going to present of embedded fractures in a grid, in a simulation grid. And in another poster, Arthur will present a multi-scale model for unstructured grid. So you are invited to check these posters as well. So for this work that I'm going to present, we are going to the finite element embedded with fractures. So we are going to use the strong discontinuity approach. So in this approach, we are introducing a fracture. We are mapping a fracture inside the finite element, as we have in this case a jump in the displacement field that is the fracture aperture. So in this case, we are going to consider a model, a constitutive model for the fracture, and another constitutive model for the rock, and the equilibrium will be established by the traction continuity. And so if you have change of stresses, we have change on the aperture of the fracture. And we are also able to update the fracture permeability at the element. And so the fracture permeability of the finite element will be a function of the permeability of the fracture and the permeability of the rock. And we are going to use the closure model proposed by Barton Bandes for the closure of the fracture. Similar ideas we apply when we have a barrier that are embedded in the discontinuity. In this case, we have a jump in the pore pressure field. So we are going to use the strong discontinuity approach, but for applying to the pressure field. So we can state the Darcy flow for the domain, the Darcy flow for the rock, the Darcy flow for the discontinuity that in this case has a lower permeability. And we can explicitly account for the jump, and we apply flow continuity, and at the end we can obtain the equivalent tensor for the permeability tensor for the finite element, considering the rock and the barrier. And the idea is to apply both technologies to the finite element analysis, considering coarse meshes that are more efficient. This is we validated with many numerical examples. It's one of the examples that we validation. We embed a barrier in a domain with between 2 points that we apply a pressure gradient, and you can see here this curve is the evolution of the flow with the permeability of the barrier. And we use a very refined classical finite element mesh and a coarse mesh with the barrier embedded. Here you can see in this graph that we have very, very similar results. It's very robust technique to represent barriers in this method. And we apply this technique to an analog of the post-salt faulted reservoir. This is one of the analogs that we are working. It's a sandstone of the Antônio Navarro formation in Rio do Peixe Basin in the northeast of Brazil. This is a work that we've done in collaboration with Professor César Nogueira from Federal University of Campina Grande. It's another federal university close to us. And in this outcrop, we have a core, the exposure of the core zone of a fault with the very well defined deformation bands that we could map these deformation bands in the field. And for instance, here is the area that we considered for the Utah outcrop. Is a 5 by 5 area meters that we mapped in a very well refined model and a high fidelity model, the deformation bands. And we applied this numerical simulation for 2D and 3D geometries. And the answer that I made in the beginning of the presentation is that yes, it's affected a lot, the permeability of the rock with the presence of deformation bands, but it is an isotropic, in an anisotropic way. The equivalent permeability when we apply the flow-based upscaling is very heterogeneous. We have, depending on the direction of the flow, we can have permeability close to the rock, or the permeability completely different, governed by the permeabilities of the deformation bands. So we have very heterogeneous equivalent permeabilities for the core of a fault. And depending on the direction, we can have the barrier effect due to the deformation bands. So I'm talking about now the embedded fracture technique. We applied to different problems, and I will show you this first problem that we applied. So as a Colombian fracture net reservoir is an onshore field. Sorry. It's a low porosity sandstone reservoir, and they have this reservoir has vertical, almost vertical fractures, but in an environment of high horizontal stress. So when we have production, we have the drop of pore pressure, increase of effective stress, and closure of the fractures. And depending on the stiffness of the fracture, of the closure, for the fracture closure, we can have the decrease on production. So this is a problem that is called the geomechanical damage in the literature. And you can see here the evolution of permeability that is decreasing very quickly when production starts, and the blue is very low volume. And we can see also the near well displacement field showing the compaction of the reservoir close to the well. So we apply this to a real case problem, but also to outcrop. This is a Araripe Basin outcrop that is close to the other outcrop that I showed with deformation bands. It's about 2 hours by car. And in this case, we have fractured carbonates, very nice fractured carbonates with fractures in different scales, different fractures of fracture families with open fractures, veins with mineralization. It's a very interesting environment to study. The geologists of our team of our university are studying this outcrop for many years. We can see here, I cannot point, but we can see here a karst, a big karst that we can in this vertical panel. And this is a very interesting place to study because there is a mining activity in this area. So this panel are dynamics. They are extracting material for the civil engineering industry. So we separate a block. We could isolate a block by 50 per 5 meters, 35 meters by 55 meters by 20 meters. And it was, by the way, the other study, the deformation band study, was performed by a PhD student, Franklin, and this study in outcrop, carbonate outcrop, was performed by Deborah Sees, another PhD student that already finished her work. And she had the opportunity to have a very well characterization from the point of view of geology characterization, petrophysics, and geomechanical properties. A lot of work was done in lab to characterize the properties of this outcrop. And we have this block that we could map the fractures using vertical and horizontal scan lines. And then we apply the flow-based upscaling to identify the most relevant fractures in this system. And we find that there are three main families of fractures, two vertical fractures and one family for horizontal fractures. And we found that the most relevant fractures are the vertical ones that have more connections. They are more interconnected fractures. And but then the horizontal fractures cannot be neglected in the upscaling. So we are now interested in studying this degree of interconnection of fractures. We have two PhD students, two other PhD students studying the problems related to embedded fracture to topological analysis. So this is the topological analysis of fracture networks integrated with flow simulation, with Jefferson's work that he published recently in the Journal of Structural Geology. And the idea is to identify the relevance of the fracture terminations. We can have an I-type termination, so a termination of a fault is isolated for the others. We can have a Y-type termination, that is when one fracture ends into another fracture, and we have a X fracture termination when we have the fractures crossing, two fractures crossing each other. So we have that there are numbers that characterize this hydraulic connectivity that is for a fracture network, and we propose diagrams, ternary diagrams to characterize the fractures crossing the terminations, and we propose different synthetic fractures networks to study the relevance of the interconnection of the fractures. Of course, we apply the upscaling for different types of fractures network with predominance of X terminations, Y and I terminations, and we combine them and try to understand how these terminations can be, these intersections can be influenced the equivalent permeability of the medium, and of course the X and Y terminations interceptions are much more important than the Y-type terminations, but it's important to consider depending on the fracturing density that we have for these isolated fractures. This is already published, and we have another PhD work that apply this methodology to a real case for a pre-salt reservoir. This is this figure. You can see a grid cell for the pre-salt reservoir that are about 55 fractures that we could, using the ternary diagram, we could identify the type of intersection that we have, and we perform different analysis to obtain information about the permeability and also the dual porosity and permeability features of this characteristics of this type of geometry, the DFN. For instance, trying to understand how shape factor could be different for different fracture intensity, fracture densities. And as we have many cells to study. And okay, just to conclude my presentation, Models that predict permeability by considering analogs have been used to enhance the understanding of the relative contribution of deformation band and fracture networks to reservoir quality. In a discrete fracture network, DFN, model topology represents the connectivity aspects of the fracture planes, which have fundamental role in the flow simulation. It has been shown the influence of fractures interconnection degree on the equivalent permeability of the fracture. You can see more details in the papers, but it was found a strong influence of X and Y topological patterns. Of course, it's something that we can feel that it's something that we can imagine that it's more or less logical, but it's important to prove with field data. It's the main idea that's of our work. And the same for deformation bands. Petrophysical analysis showed that samples affected by deformation bands are lower porosity and permeability. It has a lower porosity, and permeability. And numerical fluid flow simulation allowed us to conduct the deformation bands act as flow barriers, where the hydraulic head can indicate the barrier effect intensity. So this is the two main conclusions of the problem that we proposed to understand best the behavior of deformation bands and fractures using outcrops, sandstones, and fractured carbonates, outcrops. And just to let you know, we are now interested in working in volcanic rocks analogs that we have in our region, in the northeast part of Brazil, interested in injecting CO2 in basalts, as we know that we have a high conversion rate for CO2 to minerals. So we are interested to collaborate with you all in outcrop analysis and simulation, numerical simulation in the topics of faulted sandstones, fractured carbonates, and analogs related to volcanic rocks for CO2 injection. I would like to thank you and acknowledgement for energy simulation, Petrobras, and our sponsors. Thank you very much.
Thank you, Dr. Guimaraes. Any questions from the audience here as well as people online? So for the audience here, there's again a microphone right in the middle, or you just raise your hand. We'll see if we can get a remote wireless mic to you. So far, I haven't. Okay.
Hello. Good morning. I'm Dennis from University of Campinas. Great work, Leonardo. I was wondering how we could incorporate all this knowledge in commercial simulators. Can you talk about that in our commercial simulators used for pre-salt in Brazil?
We are working on this. There are different ways to incorporate. We have, for instance, we can include the discontinuities, fractures, as the kind of elements that they have in the transmissivity of the elements between the cell blocks. There is a work that is doing on this, and when we consider, so it's a way using finite different codes that we can embed as well a fracture. And when we are considering geomechanic effects, we are using the pseudo-coupling approach, where you build tables for, we do this upscale, the numerical upscale to obtain the equivalent properties of a cell. And then we build a table for change of porosity, permeability, and other properties that we want, that this is available in the simulation codes, that we can have the dynamic porosity and permeability as a function of pressure, but with information of geomechanics. So in fact, we have one of the projects that we have with Petrobras, we are building tables for fractured media to be applied in the using the pseudo-coupling technique.
Okay, thank you.
Okay, thank you. There's a question online here by Master Irani. The question is, any comparison on how much is different between dual porosity averaging in numerical simulation and DFN results? How can we upscale this, and any idea how much wrong we are?
Well, we build for a procedure to take into account to calculate all the properties that are needed to the double porosity and double permeability models for a generalized fractures that we can apply to the simulator. And in fact, we are one of the aspects of the Laura PhD thesis is to check if given a fracture network, what is the suitable formulation. It is a single porosity permeability or double porosity permeability. And more than that, if you are having a dynamic fracture aperture, there are situations that we found that we can begin with open fractures with a very clear double porosity permeability simulation that during the production we have changed in the aperture, and we have a single porosity. At the end, you can have single porosity permeability and porosity. So it depends on the case, and we have to apply the procedure for case by case.
Okay. Here's another question online before the in-person question. This question from Vijay Srivastava, who represents CMG. How do you generate tables for the pseudo coupling? What are the parameters? We consider the pseudo coupling. We have a high fidelity model with all the geomechanical information. So we perform the upscaling, flow-based upscaling, considering the geomechanical and flow properties with high details. But the output is only a table that is porosity permeabilities, porosities and permeabilities as a function of pressure. It's only what the commercial code have available. If the commercial code put more information in as a function of other variables, you can also generate. But in our procedure to use the commercial codes, we consider all the complexity, in the cell that you build the tables in very much. Of course, we cannot guarantee that all the information in the high fidelity model will be in that table. It's an important aspect in the limitation of pseudo coupling simulation. Okay. One last question from the in-person audience. Please state your name and affiliation.
Doug Beringer, retired. Your topological upscaling, the formula looked to me like it just had a number of elements that it was counting in various directions. What about the effects of stress anisotropy, or it could be the diagenetic history of the fractures too? Can you incorporate some kind of transmissivity or conductivity for the fractures in that upscaling?
Yes, if I understood, we are asking about the incorporation of stress state.
Stress state, or
Yes.
maybe even mineralization, whatever character fits to each set.
Each physics depends on the. We are doing for this upscaling that we are doing is applying different stress states in the outcrop case block, that big block that we build, that we apply different stress states analogous to the stress state of the field that we have. So we have to consider this information, and when you build the table for each pressure that we calculate the equivalent properties,
they are considering the stress state of that cell in the field. So the total stress is constant, but the effective stress is changing because of the pressure. So the fractures are open and closing.
Yes, in the simulation, but in the topological upscaling that looks at connectivity.
Oh, it's
is it
more,
considered
it's
there?
harder. It's harder to consider. I understand. Yes.
Yeah, I would think that would be a great
It's not.
addition if
Yes,
you can put it in there.
it's important. We are not doing yet this for the topological analysis. Not the. But
Thank you.
It's very interesting. Thank you.
Thank you. Good questions. Once again, thank you, Dr. Guimaraes, for the talk.